the last lecture, we introduced the notion of simulation, how probability information about events can be combined in order to model business situations. We're now going to explore simulation in more detail to give you a fuller feel as to what's involved with simulation. As an overview to this lecture, I will cover the 4 points. First of all, what is simulation? Next, why simulation is useful in business situations. I will next cover the steps involved in Monte Carlo simulation, and we're going to be simulating then the revenue for a product launch in some detail. First of all, about simulation. Simulation models in real business situations are done and obtained through using, typically today, spreadsheets. And what we have is an add-in to a spreadsheet, such as an Excel or a 1, 2, 3, that enables us to extend the utility of a spreadsheet to simulate business circumstances. Popular packages for simulation modeling, Monte Carlo simulation modeling, include Crystal Ball or At Risk, and many others have been developed in order to enable business managers to get their hands around the risk and uncertainty of business situations. As an example of a simulation, I'm going to simulate a slate of films to show you how it would work in a studio situation, a movie studio situation. What we're going to do is we're going to build a computer model, and we're going to play a game. We're going to, as it were, let the studio live 100 lives or 1,000 lives to see what the slate of films would produce. And as we let the studio build 100 slates of films or 1,000 slates of films, we get our hands around the possible range of values associated with the slate. And also, we get the probabilities associated with each slate revenue occurring. Let me illustrate this by setting up a specific model here. If I go back to the green board, you'll notice that what I have done, I've set up a very simple slate of films. Now, a slate simply means a portfolio of films. A studio may do 10, 15, 20 films in a year. Here I have a simple slate of 5 films, 1, 2, 3, 4, 5. Okay? And what I'm tracking here is the revenue for each film. In this case, we'll keep it simple and keep it to be domestic box office. That means what you pay when you go to see a film in the theater domestically here in the United States. Now, I have to start out by building my spreadsheet model. And here is my spreadsheet model. Let's just focus here on a simple summing of the revenues associated with each film. So in film number 1, 2, 3, 4, 5, in this first slate, I assume that each one of them earns $10 million at the domestic box office for a total revenue of $50 million for the slate. This is what I want to track. As a movie studio executive, what I'm interested in is figuring out what my slate will bring me for the year in domestic box office. Now, in order to do this, what I do is I put a distribution. I put a probability distribution, an assumption. Think of it as an assumption behind each of these cells. And that assumption relates to how individual films are distributed in domestic theatrical box office. And here's, for example, a sample probability distribution. And we'll talk more about distributions as we go forward in this class, so you get a feel for how distributions work. This one is not symmetrical. Notice we talked earlier about the fact that this is skewed. This is skewed to the right. Remember, a skewed to the right distribution means that its tail goes off to the right. Here, the mode, or the highest point, is approximately $10 million. That's where the peak of the distribution is. Remember, the height of this distribution relates to the likelihood of that value occurring. And the most likely value is around $10 million. Notice this distribution, as I said, Tails off to the right. Here I can get a breakout film, and we have a breakout film being defined as maybe $100 million in domestic theatrical box office. I can even go higher than that. I can have a Forrest Gump or some type of movie which really breaks out extendedly, and because this distribution can go on, but it's relatively unlikely for that to occur. Notice I can also have a bust. A busted film would be down here in the low end of the revenue distribution, maybe 1 million at domestic theatrical box office, or even less in some cases. So this describes the individual film assumption that stands in my model that I'm going to use as a basis for building my simulation. Now let's back off and take a look at what I'm doing here. Behind each of these cells stands this distribution. This distribution sits behind each of these individual 5 films. And it's going to be recalculated every time the spreadsheet is what we call iterated or recalculated. And the probability of a value coming up will be driven by this underlying assumption. For example, let's look at, now this first slate, I've just forced every film to be the mode. Now that's very unlikely to occur. Even though the modal value is the most likely individual value, it's very unlikely that all of these films will just kind of look modally. So here's slate number 2, which may be a little more typical of a slate. So now this is another iteration, 1, 2, and I'm going to the second slate in the film, second slate in the simulation. Here the first one is 8 million. It's right about here. The second one is a breakout. Something happens, something exciting occurs, and I get a film that returns 120 million at the box office. And as I was mentioning, this is what movie studios live for, to be able to get these breakout films. Then I have a bust. That's the way life works, right? Sometimes you get the breakout, sometimes you get the bust. Then I have 2 films that return 50 million. The slate total is 230. Then I run it again. Now, the Monte Carlo simulation that's inside the computer is going to do this as many times as you tell it to do it. Maybe it's 100, maybe it's 1,000, maybe it's 10,000, depending on the complexity of your model. The overall goal, once again, is to get some sense of how likely it is that each of these values will occur in the slate total, which I'll show you in just a minute. Here's another slate, for example, slate number 3. First film is 30, second film is 20, 10, 10, and 20 for a total of 90 as a slate total. Once again, these values are independent and they are generated according to the underlying film distribution that is for each individual film. So you might ask the question, how do you get that individual film distribution? And here you may be looking at historical information that you're tracking past films as to how they performed for you or for your studio. But somehow you have to get this initial probability range or distribution. We talked about this earlier about the different ways that people can obtain probability estimates. So you obtain this individual film distribution and then you build these slates of films. Now, where it really becomes valuable, and we'll look at this in more detail when we study the product launch simulation in just a few minutes, is when I look at the total revenue for the slate. This distribution down here tracks each of these totals and builds a histogram related to the slate total. So this is the domestic theatrical revenue for the entire 5 films. Of course, I could build a model for 10 films or 20 films. And in the real world, when you build models like this, you include multiple revenue lines, including domestic theatrical, foreign theatrical, pay-per-view, and all the other revenue lines which come into the model. And film studios, when they build models like this, they get relatively complex to be able to try to accommodate the reality of the business situation that the film studio is working towards. Because once again, as we said periodically and repeatedly through the class, a model is good to the extent to which it approximates the reality of the business situation we're trying to approximate. No model will be perfect, and a model is a reduction tool, a simplification tool, but it helps us once again to get our hands around the uncertainty that we're dealing with in trying to predict the future. So here's a slate total. For example, in the 50 class, this one would go somewhere down here. It would help build the height of this histogram. 230 would be way out here, where I had this breakout. So this is a histogram that is generated as a forecast for the total revenue related to my slate. And once I see this, I've kind of, maybe I can sleep better at night if I kind of know the extent to which I can get this spread. What does this spread look like? What's the worst case situation that occur with this slate? What's the best case? Now, if a bank wants to loan money to finance films or for whatever project we're talking about, that I'm giving you an illustration in films. In the movie industry, simulation is used in a wide variety of industries today. I might want to particularly look at this downside for probability, so I know how bad things can get as to how much financing I may have to, and how certain the financing is and how risky the financing is. On the other hand, I may also, if I'm the executive and I'm talking to investors, I may also want to say, well, yeah, there's downside, but there's also upside potential in dealing with this in this slate. So what we have here when we deal with Monte Carlo simulation is we are essentially allowing this studio to live 100 lives or 1,000 lives this year and to see what the range of possibilities is, and also to see the probability associated with each range. Now, a word about Monte Carlo simulation because it has historical roots. Monte Carlo simulation, it's called Monte Carlo simulation because random numbers are selected for each assumption cell, just like spinning a roulette wheel. When I say spinning a roulette wheel, the roulette wheel is not totally fair. The roulette wheel is driven by the underlying assumption that stands behind the individual film. This determines the probability of any number coming up. On a roulette wheel, if it's fair, you have an equal probability of getting a 1 through 36 or 0 or 00. Here, the numbers that come back are not evenly distributed. They're not uniformly distributed. What occurs is that the number that we obtain is driven by this underlying assumption, this underlying distribution. But that's the way we want it to be. We want it to be that way because we believe that this is the most appropriate representation of the individual films that we're producing. We don't know. We're not smart enough to know exactly how a film is going to do. We're not intelligent enough to say this film will exactly do this amount of revenue. All we can say in this model is that if we produce a film, the probability of it returning a certain revenue is related to this distribution. That's all we can deal with. Now, and it turns out that if you build a slate of films, you can obtain a distribution which is tighter. It's like diversifying a portfolio of stocks. That if you start to diversify, you're going to, on average, have a good one and a bad one, and then you can see the risk of the entire slate or the entire portfolio. In fact, as we'll see later on in the course, we can say a lot about this distribution of sums. In fact, we will see that there's a classic theorem called the central limit theorem, which will enable us to say a great deal about a distribution of sums that are selected from any beginning distribution. But I'll save that for another lecture. We'll come back and deal with the central limit theorem because it is very significant in describing how distributions work when we take sums or averages of individual selections out of a distribution. Monte Carlo simulation was a term coined by John von Neumann and others in developing computer simulations related to the simulation of nuclear fission related to the testing of the atomic bomb in the period in the 1940s. It started off in physics and has now evolved into many applications related to business and many other areas of engineering. a simulation is used to try to deal with this uncertainty dynamics. It's used not just in slates of films. Monte Carlo simulation is used in oil and gas exploration. It's used in, say, projecting revenue for a new venture or for a new product, for doing a net present value analysis on an initiative, on an expansion, let's say a new geographic location for a law firm. I've seen it used. What's the range of, should we make this move? We're now in Boston. We were thinking about expanding to New York. Should we make the move? How do we simulate the range of possibilities? It's used for product marketing, product advertising for companies like Procter & Gamble or Clorox, inside companies which have commercial products to be able to analyze the impact of advertising campaigns and see what the likely response is. Monte Carlo simulation is not the only way to build models. When we talk about model building, we're talking about a very wide range of tools that we pull out of a tool bag. But Monte Carlo simulation is one technique that I want you to be aware of because it is closely related to the probability theory which we have developed in the last couple lectures. And rather than simply just talk about textbook probability problems, I want to show you how to extend some of these notions to be more closely match business situations. So let me review the steps in simulation. There are 3 steps, and the illustration I gave you on slate revenue illustrates those 3 steps. First of all, you develop your assumption cell. And that's what I did over here. I took the assumption cell related to an individual film, and I somehow modeled it. Now, it turns out that this is a very simple model, and I have one assumption. When I build a simulation, I may have different assumptions in different cells inside my spreadsheet. But the first thing I must do is to develop my assumption cells. I may have 10 of them, and they may not all be the same. Here I have 5 of them, but they're all the same. I may have 50 of them inside of a spreadsheet. They may be different if I am trying to model a relatively complex phenomenon. Then what I do is I calculate the spreadsheet n times. Now, n may be 100, as I said. It may be 1,000. It may be 10,000. And each time I recalculate the spreadsheet, no, I don't do this. The computer does it for me. I set that number inside the computer, and the computer automatically spins out 1,000 future realities, plays my game 1,000 times, and each time it tracks this slate total for me. And as it tracks this slate total, it's building this distribution. So I get a picture of the forecast, because this is the final step. The final step is viewing a forecast chart, or charts, because I may want to view not just revenue. I may want to view, if I'm a bank considering whether to finance this portfolio of films or not, I may want to track what the bank loan will be if I have to adequately finance this company going forward. So here I'm tracking, though, domestic theatrical revenue, box office. And that's the forecast cell. So these are the 3 steps involved in simulation. You develop your assumption cells. You calculate the spreadsheet n times, and you set n to be whatever you want to be. If it's a very complex model, n may be as large as 10,000 or 50,000 times to see the full spread of possibilities associated with my simulation. And then I view the forecast chart. Now, let me next talk about our revenue forecast model so that you see in a little bit more detail what's going on here. In the revenue forecast model, what we're trying to do once again is forecast sales revenue for the year 1997. Notice this is a product launch that we're considering, and we're trying to ascertain what the spread is in forecast revenue. I am not certain whether or not a competitor is going to enter my market. I don't know. In fact, maybe where we should start is looking at the assumptions associated with this model. One of the assumptions certainly has to be with the competitor entry. And let me build here some of the assumptions that are present. As far as the competitor entry is concerned, we will assume that this is a yes or no decision. And for purposes of simplicity, let's say it's a coin toss. I don't know whether my competitor is going to come in. Therefore, I am going to assign an equal probability to a 0 or to a 1. 0 meaning no, the competitor stays out of my market. 1 meaning the competitor enters. That's the beginning point of our definition of assumptions. Now, I also am not certain, there's lots of uncertainty in my model. I am not certain about what price will be able to be sustained in this market. So if the competitor doesn't enter, though, I will be able to charge a higher price for the product. And the price, therefore, for the non-entry is maybe looks like this. The most likely value is 70. And I am, I can draw any distribution here that I'd like. I might be able to charge, say, up to 110, but it may be forced to go down to 50. And this is what's known as a triangular distribution. And as I was mentioning yesterday, pessimistic, most likely optimistic business people kind of like to think this way. It's not necessarily a formal statistical distribution, but here the value that will be returned in each calculation of the spreadsheet is proportional to the height. 70 will be much more likely to be returned than, for example, 45, because the roulette wheel is spinning, and the number that will come back is proportional to this distribution. Here the roulette wheel spins, and it is going to return a 0 or a 1, and they're equally likely for the competitor entry. Here, for the revenue with no competitor entry, is what the distribution will look like. Similarly, the revenue for a competitor, if a competitor enters, may look quite similar to this, except that my most likely value might be slightly lower. It might relate to 50 being my most likely, and I may have to drop my price to 30. And maybe I'll be able to get up to 70. So this is with the competitor coming into my market, and this is without. So my underlying distribution varies substantially given the circumstances that I'm dealing with. Now, as far as my volume is concerned, my volume also may be suspect or subject to the fact of my competitor entry. So, for example, my volume with no competitor might look like this. It may be, as we'll see, what we call a normal distribution. Now, the value may start out at around 5,500 as my modal value, and it may be what we call normally distributed. It may look like this. We'll discuss the normal distribution in more detail in another lecture, because it turns out that the normal distribution is very special. It comes up time and time again. It just kind of repeats itself. And it shows itself up in all numerous business situations. So we have to understand how the normal distribution works. And we have a special lecture devoted to that distribution because we really want to know how to work with this one. This may be the volume with no competitor, without the competitor. Now, I may have also a similar normal distribution associated with the model if the competitor indeed comes into the market. So how this revenue forecast model is set up so that you see what's occurring is that there is a price with no competitor that is an assumption. That assumption is a normal distribution, or is a triangular distribution such as I've modeled. Let's just assume that it's triangular. There is a price if the competitor enters the market. That too is triangular. Then there is a volume associated with no competitor coming into the market and with the competitor into the market. Notice the volume that I have in this initial model is less. I'm assuming that I'll be able to get less volume if my competitor enters. Now, that's not always the case. It could very well be that a competitor enters the market and the whole pie gets bigger for everybody because the market is made, so to speak. Oftentimes in business situations we see that occurring, that sometimes people feel competition is unhealthy, but in fact what happens is competitor enters the market and the market awareness gets going. And particularly, here you see like IBM entering the personal computer market in 1981 or whatever. the time frame in the early 1980s. I guess it was actually 1984, that time frame. What occurred was that the whole market started to get larger for everybody as a result of a large player putting their stamp on this market. What occurs next is the competitor entry. It's a switch, yes or no. It's either on or it's off. And if it's off, it's 0. If it's on, it's 1. So I'm putting together some conditions now upon this market. And notice in the model that finally I extend down and there's an actual sales price and an actual sales volume for each recalculation of the spreadsheet. So if you look at the slide which deals with one iteration of the model, now I start recalculating the spreadsheet. And here is one calculation. Let's see what happened with this first iteration. And all iteration means is a step, a recalculation of the model. I'm doing it one time. I'm letting this product live one life. I'm going to let it live thousands of lives, in this case maybe 500 lives. And I'm going to see what the revenue associated with this is from a probabilistic standpoint. All right, here we go. One trial of the model. $81 is the price that it can be sustained. So what happened in this is that, notice first of all, the competitor did enter the market in this case. The competitor did enter the market, and I was able to gain, if you look at $57 was the price that occurred if the competitor entered the market. So what happened was the roulette wheels was spun, and the value that was selected in this one was about $57. It was a random process, and that's what the model selected for the competitor. Now, how do I know that the competitor entered the market? Well, because there is a 1 when it says competitor entry. It either could be a 0 or a 1. In this case, the computer spun the roulette wheel, and 1 was selected. It was a coin toss. Well, the computer tossed the coin for me and picked the 1. Now, once the 1 was selected, the sales price that the model uses is conditional. Remember, yesterday we were talking about conditional probability. That what occurs, that given the fact that the computer has said that the competitor entered the market, the sales price that I can sustain is $57. So that's what the model puts here for sales revenue. Same comment about sales volume. The volume that was selected in this case was 3572, reflecting the fact that the sales that the competitor has entered the market. These are both conditional cells that relate to the fact that we have a competitor. And the values that are selected are driven by the assumption cells that are related to each individual cell in the model. So let's review this model. We have 5 different assumption cells. One related to computer entry, to competitor entry. That is a discrete distribution, a coin toss. 2 related to price. Those are triangular distributions which relate to pessimistic, most likely, and optimistic. Then there are normal distributions related to the volume. Now, I did not draw the normal distribution associated with the competitor entry, but it's very similar to what you would see with the one without the entry. And what happened in this case was that the model selected a competitor entering, and the revenue associated with this run of the model is $202,533 for my product. That's one calculation of the spreadsheet. I'm going to do this 500 times. I'm going to do this 500 times, and if you turn to the next slide, you'll see that what I have here is a forecast chart. A forecast chart which relates to 500 trials. 500 trials of this revenue simulation. And this is a histogram which shows the range, not only the range, but the probabilities associated with each range, with each value of the revenue. So here I have 1997 revenue, 500 trials, and notice that as I was saying in the previous lecture, that I almost have two humps to this. And it's almost describing, and these humps are somewhat related to the fact of whether or not the competitor enters the market in this particular model. It wouldn't have to be this way, but this is the way this model works. And notice that for each revenue band, I get the chances. The y-axis, or the axis going up, reflect the chances or the probability of getting inside that particular revenue band. So if I wanted to ask questions such as, what are the chances of getting between $200,000 and $300,000 in revenue associated with this product? I could answer that question given the fact that I have all the probabilities associated with those bands. Just like with the slate of films, I can ask questions now such as, what are the chances of getting between $100 and $200 million in slate revenue? Well, the chances are just the sum of all these probabilities. Each of these represents a probability for being inside a revenue band. So I can ask a whole host of questions. I can ask questions, for example, what are the chances of getting more than $100 million in revenue in the slate? And the chances would be the sum of all these probabilities to the right of $100 million. Or in the forecast revenue chart, I could say, what's the chances that this product is going to return me more than $300,000 in revenue? It would be the sum of all those probabilities to the right of $300,000. Or I can ask the following question. I want to be 95% confident of the range. What that means is the following. As we've been saying, that sometimes some very extreme events can occur, some very unusual happenings. For example, in this slate, it's theoretically possible of films, the slate of films, for every film to be a bust. It's theoretically possible that I get a 1, 0, theoretically could be 0, very low probability. Let's say it's theoretically possible for me to get a 1, 0, 1, 1, 1, or to get 4 million in the slate. Very unlikely, but it could happen maybe once in a million years or whatever. It could occur. Just like it is theoretically possible for, as I mentioned yesterday, for someone to drive a 550-yard hole in a hole-in-one, or to miss a quarter-inch putt, a professional golfer. It could occur. The chances of it occurring are so remote. So sometimes what we do, we say, wait a minute, let's eliminate those way-out events. Because those way-out events, hey, I can sleep at night not worrying about those, because the chances of them happening are so very, very remote. So what we do sometimes is we take the tails of the distribution, the way out events. Now I haven't even drawn. It could. Let's say I got 5 breakout films. Let's be optimistic. If I had 5 breakout films out of 5 films, I mean, that would be a phenomenal occurrence. It's never happened in Hollywood. But I would be way out here, and I would have $600, $700, $800 million in domestic box office from the slate if they were all more than $100 million in domestic theatrical revenue. I may want to say, wait a minute, let me cut off some of those tails. And what I've done in this forecast chart for 1997 revenue is that I've cut off 2.5% probability in each tail. I've sliced the distribution. Now, when you slice off tails in a distribution, you get what we call a confidence interval. And what that means is, well, let me go over here and show you what I mean by slicing off the tails in a distribution. What occurs typically is that here's my distribution of values, whether it's a product launch or slate, domestic, theatrical, I don't care. But let me just draw the distribution, maybe say it looks like this. There's some very remote values out here. What I want to do is slice off the tail so that what I have left is 95% of the probability. And so what I'm saying is that 95 times out of 100, I will be in this range. And I might be able to sleep at night. Notice in this case, the full range goes down almost to 100 million and up maybe to 460, 470. But when I chop off the 2.5% in each tail, the range goes from 146 to 463. I've eliminated some extreme values, and I'm 95% confident that the slate total will be within that range. Now, let me tell you that sometimes in some situations you're able to sleep with even less confidence of that. 90% confidence. If I had 90% confidence, I would chop off 5% in each tail. 80% confidence. I would chop off 10% in each tail, and I would be right 4 out of 5 times. 80% of the time, I would be correct. And maybe, just maybe, I can sleep at night with that type of range. Now, this is a subjective judgment to determine how comfortable you have to be. I have seen sometimes business executives say, just give me a 60% confidence interval and chop off 20% in each tail, and I will be right 3 out of 5 times. And I guess I can live with that range. Now, a bank might not want to live with that range, but sometimes an executive will be willing to live with that type of range. So maybe a 90% confidence interval would be just good enough. Now, there's one final notion that I want to leave with you before we conclude our discussion of simulation. I want to differentiate one thing so that you see a distinction between sensitivity analysis and simulation. Maybe you've heard the term sensitivity analysis. Let me differentiate for you, very briefly, sensitivity analysis and simulation. Now, with sensitivity analysis, what you do is you build a table that looks something like this. Let's say you're talking about a business, and here you have your revenue growth, and maybe your business grows at, there's 3. We could be flat, we could grow modestly, or we could have hyper growth. Okay? And maybe also I want to track my receivables collection, how quickly I will collect my accounts receivables, what people owe me. How quickly will the credit I've extended to people, how quickly will that come back to me? That's what we call an accounts receivable. And maybe I'll collect my receivables in 30 days, 40 days, or 50 days. On average, how quickly do people pay me on average? And what I really want to understand is what my cash position is going to be. What will my cash balance be in my business at the end of the year if I grow at these rates and collect my receivables at this? And maybe you get a table that looks something like this, and I'll explain it after I draw it. If I collect receivables in 30 days, if I grow at 0%, I'll have 140,000 in the bank. If I grow at 10%, 130, 50%, 120. Now you might say, how come you're getting less? Well, my revenue growth is sometimes sucking up cash. It costs me to grow my business in cash because I have to invest to be able to grow the business. You often see this occur. If 40 days, I'll have less cash, and I won't necessarily complete the whole chart. It may be in a very worst case situation that I have a negative cash balance. And if I grow this business at 50% and I collect my receivables in 50 days, my customers are slow in paying, I will have a negative $20,000 in cash. I will not have enough cash to run my business if I allow this scenario to occur. This is what we call a two-way sensitivity table. 2 ways because I have 2 dimensions, revenue growth and how quickly I'm collecting my receivables. Let me differentiate for you between a sensitivity table and a simulation. First of all, notice that a sensitivity table gives you no probability estimates. I have no way of knowing whether or not this $100,000 ending cash balance is more or less likely than this negative 20. Now, sensitivity tables are useful because it kind of allows you to key on 2 dimensions, maybe 3. But normally, sensitivity tables are 1, 2, or 3 dimensions. And consequently, I'm able only to key on 2 variables, or 3 variables. But I do not know the probabilities associated with each of these variables. In each of these, I do not know whether or not either one of these is more likely than the other. All I have is the value. I don't have the probability associated with the value. Also, simulation allows you to vary a large number of assumptions simultaneously. For example, in this movie model, or in the revenue generation model, we could change more than 2 or 3 variables at the same time and see what happens. Sometimes complex simulation models may have 50 or 100 variables changing at the same time towards the end of making the model fit my business reality and deal with the subtleties of business. So what I'm suggesting to you is the following. Both simulation and sensitivity analysis are useful techniques. However, simulation allows you to vary a large number of assumptions simultaneously, and it gives you probability estimates for each of the various possible outcomes. So I have not only the outcome of the analysis, but also the likelihood of that outcome. And in business, as I've mentioned earlier, entrepreneurs or venture people inside of corporations not only like to know outcomes, but they like to know likelihoods, because successful business oftentimes involves stacking the odds in your favor, of seeing what the likely outcomes are and says, all right, now I'm going to do this because the odds are stacked in my favor to proceed to go forward with this initiative. So let's tie this lecture together and say the following. Simulation is built upon probability theory, that understanding how probabilities work and distributions are built is an essential element to building a good simulation model. And simulation is indeed a useful technique for modeling business situations with uncertain conditions. And whether or not we like it, we're living in worlds of uncertainty. And although simulation models may not be the end-all to be able to help us deal with risk, in fact, sometimes what we must do is make decisions even with uncertainty, considerable uncertainty, because simulation model does not give us an absolute answer, and sometimes we have to intuitively come in and decide what to do. We have to use both analytical power as well as intuitive power to decide where we should go, how we should proceed. The classic metaphor that was used quite commonly was the fact that Luke Skywalker comes in and the Death Star at the end turns off the computers and goes with, quote unquote, the Force. And sometimes business people have to do the same thing. However, the extent to which you are able to get good analytical information, to refine your intuition, to build it, to enable you to feel more comfortable with going forward, is the desirable way to go.